Hello. Now we're going to continue our work in probability, and we are going to be talking about events that are mutually exclusive, or tests for when things are mutually exclusive today. So let's talk about the words for a moment. If we look at just the English of these things, mutual would mean together, and exclusive means to exclude or to not allow. So mutually exclusive means two things that exclude each other. And in more common English, two things that cannot happen at the same time. So two descriptions that have no overlap, two things that cannot happen together. So if outcomes A and B are mutually exclusive, if they can't happen together, put another way, no single outcome that we'd look for can fit both requirements or both descriptions. As an example, we can't get if we're looking for a black or a white marble in one of our questions where we have marbles in a bag and we are asked to pick out a black or a white marble, there's no marble we could take out of the bag that would be both black and white, that would meet both descriptions. So saying that, we would say then that getting a black or a white marble would be mutually exclusive events, because we can't have a marble that is both black and white at the same time. So the two events cannot happen together. Now, to put a more concrete idea on this, we're going to have a look at question 4 on page 202. So don't worry if that wordy introduction isn't totally solid for you yet. Hopefully it will be after we've worked through question 4. So, in question 4, we're told a number is selected at random from the integers 1 to 12 inclusive. Find the probability that the number is part 1 even. So part 1, an even number. In an exam, you write out the list of numbers. This is extremely important. Do not attempt to do these types of things in your head. Also, if you can't remember how to do the probability question and you write down the list of numbers from 1 to 12, in a lot of years you'd get marks for doing that. So what I'm going to do is write out my list of numbers, and I'm going to underline each even number in my list and then count them up. So I have a total of 1, 2, 3, 4, 5, 6 even numbers out of a complete total of 12. So I have a probability of a half of getting an even number if I'm picking a number at random from my list from 1 to 12 inclusive. And in part 2 it asks you for the probability of getting a multiple of 3. So I have abbreviated even to being capital E and multiple of 3 to being M3 for multiple of 3. Again, writing these out so you can keep track of what your argument is extremely important. Now, just like for my even numbers, I'm going to put a mark underneath each multiple of 3. I'm going to put a circle or dot. So I have 3 is a multiple of 3, 6 is a multiple of 3, 9 is a multiple of 3, and 12 is a multiple of 3. So I have 1, 2, 3, 4. 4 out of a total of 12 outcomes are multiples of 3, and when I simplify that down I get a third. Part 3. We're asked for the probability of getting an even number or a multiple of 3. Now we're used to the situation where if we wanted to know the probability of getting an even number or a multiple of 3 or probability of A or B happening, we just add our probabilities together. I've said it to you multiple times in this chapter. Or is going to mean add. So if we do that naively for a moment, pretending that we aren't suspecting that something different is going to happen, we just add our probabilities together. Sorry, I wanted to write that out algebraically for my first line. So probability of even or multiple of 3 with probability of even plus the probability of a multiple of 3. This is what we have already done in lots of questions. So that would be probability of a half plus probability of a third. When we add those together, we're going to get 5/6. Now, what's our issue? Why is this not right? Well, I'm going to show you multiple ways of looking at how we know it's not right, but one of them comes from our list. We know that the probability of getting an even number or a multiple of 3 should be counting up all of the numbers that meet that criteria. So I don't mind if it's even or a multiple of 3. I want to know everything that meets this criteria and divide it by 12. So I have 1, 2, 3, 4, 5, 6, 7, 8 numbers that meet this criteria. So 8 out of 12 would simplify down to 4 out of 6. So I have a problem here. I should have 4/6 and I've got 5/6 instead. So I have a problem. This has not worked out the way I wanted it to. You can probably see what's going on based on my sketch here. I have 6 is in both groups and 12 is in both groups. So in effect, I am double counting. I'm counting twice my outcome of getting a 6 and my outcome of getting a 12. I'm double counting where they overlap, where the number 6 and 12 are in both groups. So what I need to do is take away the probability of getting an even number and a multiple of 3. So remove, we'll say the dots, remove the double counted number. So I'm only left with 1 6 and 1 12 counted up in my groups. So taking that away, I would have 2 out of 12 are in both groups, are even and multiples of 3. So that's going to be taking away 1/6. And when I do that, I find that I get my correct answer of 4/6, or 2/3 of my numbers. So by using my list, I actually avoid this problem, and by using Venn diagrams you can avoid it as well, but we will be able to get questions on the exam where drawing Venn diagrams or drawing a list will be very difficult. So what we're going to do is talk about it in algebraic form as well. So the probability of getting an even number or a multiple of 3 would be equal to the probability of getting an even number plus the probability of getting a multiple of 3 minus the probability of getting an even number and a multiple of 3. And this is coming from the fact that we were double counting the probability of getting an even number and a 3. We were double counting 6 and 12 because they were in both groups. Now, that's question 4 as it appears in the book, finished. That's your final answer for part 3. I'm going to use this as an opportunity to show you how the Venn diagrams work and hopefully give you a little more intuition on this part here. So if I draw my Venn diagram here, I have my anything inside my circle of even is going to be an even number. Anything inside my multiple of 3 is going to be multiple of 3. Anything inside we call this the intersection, or even and multiple of 3 is going to go here. And as we know, when we fill in our Venn diagrams, we always start in the middle. So I have 6 is in the middle and 12 is in the middle because they're in both groups. I'm inside the circle even and I'm inside the circle multiple of 3. So 6 and 12 are in both groups, they're in both circles. Next, when I've filled in the center of my Venn diagram, I then go outward and I say what's just even. So it's an even number but not a multiple of 3 would be the number 2, 4, 8 and 10. And multiples of 3 that aren't even, we're going to have 3 and we're going to have 9. And I'm not done because there are some numbers from 1 to 12 that I haven't used here at all. I have the number 1, 5, 7 and 11. 1, 5, 7 and 11. And as you can see, I've put a dot next to every single element that I've put in these sets. So remember, Venn diagrams are pictures of sets. And I have to put a dot next to each one of my elements in the set. That's one way of writing out our situation here, and you need to know how to do it. And writing it in set notation, probability of getting an even number or a multiple of 3 would be the same as, using set notation, we want everything that is in even and multiple of 3 inside these circles. So that would be the same as union of even and multiple of 3. Again, that's equal to the probability of even plus the probability of multiple of 3 minus the overlap, and our name for the overlap in sets is intersection. So that's this written out in set notation. So probability of even or multiple of 3 is equal to the probability of even union multiple of 3. So our symbol here that looks like a smiley face is union, and our symbol here for intersection is the same as and. Even and multiple of 3. Now, that's pretty much everything. I'm going to show you the other two ways that Venn diagrams can be written, just to remind you. You already know these, but here we have 4 elements in the part of even that is only even, so even but not multiple of 3. There are 4 elements in that set. Now I'm counting the number of elements, the cardinality of this part of the set, so the cardinal number of this part of the set, so I don't need to put a dot. Here I have 2 elements, here I have 2 elements, here I have 4 elements. That's another way of writing my Venn diagram. And the final way is probability. So if I have 4 here out of a total of 12, that would mean I'd have a probability of a third of being even but not a multiple of 3. Here I'd have 2 out of 12, which would be a probability of a sixth of being both even and a multiple of 3, or even intersection multiple of 3. Here again I'd have 2 out of 12 would be a sixth, probability of a sixth of being a multiple of 3 but not even, and out here being neither would be 4 out of 12, which would be a third. So I have a probability of a third of being neither even nor a multiple of 3. And if I look at all of my, just as an aside, if I look at all of my probabilities, a third, a sixth, and a third, if I add all of those together, the sum of all of my probabilities I know must always add up to 1. And again, this is a key fact that we come back to multiple times in this chapter. So, the last thing I want to talk about is, are these two outcomes, being even and being a multiple of 3 for this given list, are they mutually exclusive? Will we come back to what mutually exclusive means? Can they happen together? Well, they can, because I can see that they can happen together if I get an outcome of 6, and that both of them can happen together if I get an outcome of 12. So there are outcomes that fit into both groups, that fit into both descriptions of being both even and a multiple of 3. Therefore, they're not mutually exclusive. And the way that we can test for that, as we can possibly predict, is to see whether the probability of even intersection multiple of 3 is equal to 0. Is that true? And no, it's not. Therefore, they're not mutually exclusive. If our two events were mutually exclusive, there would be nothing in this intersection, because they couldn't happen together. These are the outcomes that can happen together. They're in both groups. So if there is an intersection of our two sets, then they are not mutually exclusive. So mutually exclusive sets in a Venn diagram will be two separate circles, A and B. So these two events, A and B, would be mutually exclusive